What is the Higgs? Well, it's known as the God particle. And here's one of the gentlemen who I think baptized it as such, the God particle. Okay, here it is. His name is Leon Letterman. And he's, or he was, he died a couple years ago. And he was a Nobel Prize winner. He called it the God particle because it was like the particle that would tell us how mass comes into being. And they were looking for this particle for many years. And apparently, the argument is that they were successful. Okay? And someone got a Nobel Prize for doing that. Okay? And so the question is, this God particle, what is it? Well, apparently it produces mass. It creates the mass that subatomic particles have. Okay? So if they didn't have mass before, thanks to the good old Higgs, they do have mass. Okay? Okay, so here we have a gentleman who it's named after. His name is Peter Higgs. Okay, also won a Nobel Prize a couple of years ago because of his discovery. And we find that he wasn't the only guy around who knew about the Higgs. It says in the 1960s, Higgs proposed a broken symmetry in electroweak theory could explain the origin of mass of elementary particles. This so-called Higgs mechanism, which was proposed by several physicists beside Higgs, which makes you kind of wonder why he got the prize and not others, right? If they all came up with the same idea, predicts the existence of a new particle, the Higgs boson, the detection of which became one of the great goals of physics, therefore the God particle. Some people got upset with that name, okay? And continues here, says the Higgs mechanism is generally accepted as an important ingredient in the standard model of particle physics, without which certain particles would have no mass. Higgs first became interested in mass, developing the idea that particles, massless when the universe began, acquired mass a fraction of a second later as a result of what? Interacting with a theoretical field, the Higgs field, right? Higgs postulated that this field permeates space, giving mass to all elementary subatomic particles that interact with it. Gluons that bind quarks together confer most of the particle mass. Okay, so that's the general idea, and apparently Higgs was credited with coming up with this Higgs field, so I guess he's one of the guys who won the Nobel Prize because of that. There were a couple others, even though there were apparently many people around the planet who had the idea of the Higgs already in their heads. Okay, so here we have a couple guys who explained it in probably more down-to-earth language so that laymen can understand. Here it is. Okay, says we have these two bosons, the bozos. CERN scientists Dave Barney and Steve Goldfarb explain the Higgs boson. Okay, and they start out in their video. There's a YouTube video on these two guys. Elementary particle that has no structure. That didn't sound right in my ears. You know, what do you mean a particle that has no structure? What does that mean? It means it has no shape? I mean, you know, I have no idea, because if they say, look, it has no parts to it, it's one thing. But to say it has no structure, that also suggests or insinuates it has no shape. So that word structure would need to be clarified quite a bit. But then they continue and say, when a particle passes through the Higgs field, it interacts and gets mass. These are their words, but all these are their sentences, their statements. The more it interacts, the more mass it has. So here we have this particle that's interacting with the Higgs field, right? The more it interacts, you know, there's the bigger, the stronger, the massive, more massive, or whatever you want to call it, the more it interacts with the field, the more mass it has. Okay, that's the general notion. Okay, and it says the Higgs boson is an excitation of the Higgs field. So we have two things here. We're saying what these people are saying. On the one hand, they say it's a particle that interacts with a field. Then on the other, they say that it's the same field that interacts with itself because it's the excitation of a field. So we have, it's like water interacting with water in an ocean. Okay, we have a wave interacting with the ocean, so to speak. That's more or less the sense that they want to give you. And the more the wave interacts, the more mass it has. Meaning it's going to encounter more resistance. That's essentially the notion that Higgs and all the people who believe in the Higgs boson are talking about. They're saying, look, if it interacts more, or it feels the field more, then it's going to have more. The wave that hit the rest of the ocean is going to have more mass. That's essentially what they're saying. And so they have the field interacting with the field because the Higgs boson is a vibration of the field itself. Okay, I hope you understood all that. We have a wave of the ocean interacting with the ocean, and the bigger the wave, the more massive it is. That's essentially it. But until it interacts, until there's an interaction, some process going on, some phenomenon, some motion, until then, it has no mass. It has mass only when it interacts. Okay? And so it says, by finding the Higgs boson, we know that the Higgs field exists. That's how they proved the existence of the field, because if they could find the boson, they knew the field exists because the boson has to interact with the field. And they finally say that if there were no Higgs field, the world wouldn't exist at all. Man, Jesus, thank God for the Higgs field. Otherwise, we wouldn't exist. Nobody would exist. Okay, so this is more or less the notion. I'll put it up here, illustrated. We have all these fish, and you can also consider them as waves or whatever you want to consider them as and they're swimming against the river. So they encounter resistance, and I guess the bigger the fish compared to the smaller fish, the bigger the fish, the more mass it has, and the smaller the fish, the less mass it has. Okay, and yeah, I illustrated it this way as well. Okay, here you have the Higgs masses, all these smileys. They're not smiling very much, and they're moving against the field, and it's their motion against the field that causes them to have mass. And then allegedly, this is transferred to particles as well, to other particles as well. Okay, so they are the ones that, one way someone explained it is, assuming you were a person in a crowd, okay, and you try to move through the crowd, kind of the bigger you are, the more you vibrate or whatever, you encounter more resistance because you hit more people in the crowd. Whereas if you're skinny and you don't move as much, you don't vibrate as much, well, then you have an easier time to go through the field of people. So that's more or less the notion. But there's a little bit of problem. That's what I want you to think about, okay? If it's true that mass is a function of an interaction between the boson and the field, right? And that's what conveys mass to other particles, assuming even to the Higgs itself, then mass is a dynamic process. Okay, let me repeat that. What these people are saying is that there has to be an interaction. The Higgs boson has to interact with the field, and we're going to forget the notion that the Higgs boson is something different than the field, okay, or similar to the field, or it's the field itself. But let's forget about that. Let's assume it's a particle. So this particle is like something separate, discrete, all on its own. It's going to interact with the field. And the more it interacts, the more it vibrates, the bigger it is. Any way you want to conceptualize that, that interaction is what conveys mass to itself and to other particles. Okay, so it's got to be an interaction. There's got to be a verb in there, dynamic, motion. Without that, you have no mass. And that notion kind of contrasts with what you'll see next, okay? And it is, what is mass? So let's start there. Let's find out what mass is, what this particle of mass is simulating. You know, what concept, what thinking is this mass? Okay, that's what we're trying to get to. Okay, so we look it up and go to the Wikipedia, a good source, because a lot of people write in there, and that's the one everybody, anyways, consults, most people out there. So that's the notion that the laymen have out there. And of course, if the scientists or physicists or mathematical physicists would object to that, they would have changed that, anything that's wrong in the Wikipedia anyways, okay? And so here it is. You go to Wikipedia, it says, in the physical science, okay? In physical science, one may distinguish conceptually between at least 7 different aspects of mass, or 7 physical notions that involve the concept of mass. They have, you could say, 7 different definitions of mass. They don't have one definition that we can sink our teeth into. They have many, okay? Several. Okay, that's not a good starting point. So what is mass? Well, you look it up in a couple other sources. Respectable, you know, always respectable. And you find this. Here's Northwestern University says, mass, how much matter there is in something. Well, how much matter, how many atoms, how many particles, any way you want to look at it, that's different than what we just heard from these other people saying that mass is an interaction between the wave and the ocean, the particle and the ocean. Any way you want to see that as well, okay? We have 2 different notions of what mass is. Is mass the quantity of particles, of units, of balls, of grains of sand? Or is it an interaction between the grain of sand and something else, the field? Those are 2 different notions. You know, they don't match, these 2 notions, these 2 definitions. And again, the Eric Weinstein's World of Physics, another prominent site, says the quantity of matter contained in an object. That's what mass is. Well, quantity of matter is very different than interaction. Quantity of matter is I have 12 marbles in my bag. That's a quantity of matter. That's different than saying that the marble, hits against something and produces the so-called mass concept. Okay? And just in case, we go to find out what weight is. Why? Because weight is an interaction, okay? Apparently, according to mathematical physics. And here you see it. Several definitions exist for weight. Again, many definitions for mass, many definitions for weight. Not all of which are equivalent. Obviously, we have several definitions of weight. Obviously, they cannot be equivalent. And it says there, weight of an object, the force it exerts on its support. So, for example, you have there a scale. You put a ball on it. It's going to push the scale downwards. That we call that the weight. Okay, whenever it stops, and so that's the weight. It's an interaction. Weight, in that sense, is an interaction, and that's different than quantity of matter. Than saying I'm going to put 10 balls on the scale, or no scale at all. Just 10 balls. 10 balls being mass. How much mass the 10 balls have together. Well, it's a 10-ball mass. That's what it is. Here, this is different. This is how much one ball pushes on a scale, an interaction. Those two are two different notions, completely different. So I guess when they talk about the Higgs, they're talking about weight and not about mass, because they're saying that the ball is going to interact with the field, right? And that's going to be the result. The result of that will be mass. That's called weight, not mass. Okay? We're talking about weight. Mass is something else. Mass is quantity of atoms in the ocean. That would be mass. But weight is the interaction of one ball or particle or whatever with the ocean. And the interaction is weight. And here they're suggesting that what the Higgs is not the particle of mass. It seems like it's the particle of weight. Okay? And here we have it as a physics fact, just in case, confirmation. Weight is independent of the object's state of motion. Now we have a contradiction, because right now they said it's an interaction. Now they say it's and you have to have something moving. And now they say, no, you don't have to have anything moving. And doesn't consider any contact force. And that's because they never saw or felt the mediator of gravity, of mass, right? Of whatever confers mass upon a particle. That's why they say there's no contact. We say there is contact. The contact is through the electromagnetic rope, so they are in contact. We just can't see or touch that mediator. That's different than saying there is no physical contact. Okay, but it says when the particle, photon, right, is at rest, its relativistic mass has a minimum value called the rest mass, which in the case of the photon is known as zero. The mass of the photon is considered to be zero. Okay, so as long as it doesn't move, whatever that is, because the photon is always moving, allegedly, the light never stops, then it's got rest mass. But as the particle, the photon, right, is accelerated to ever higher speeds, its relativistic mass increases without limit. Well, we got a little problem, because now they're not talking about interaction. They're just saying speed. They're just saying the particle is moving away from something through, I guess, empty space. It's not interacting with anything. It's just going faster, faster, and faster. The faster it goes, it has more weight. In fact, more mass, they say, which is what? Quantity of particles. So I guess the photon is acquiring more particles as it moves along, or is it that it's pressing harder on the scale that's going to measure it? What is mass? What is weight? What is the difference between mass and weight? These people keep going around in circles. They say that mass, in the case of the Higgs, right? Mass is an interaction. Then they say, no, weight is an interaction, the ball with a scale. Now they're saying there has to be no interaction for weight. The particle just has to travel faster, meaning if there was a scale there, you could gauge, how much pressure it causes. And without that, they just say the faster it goes, the more it weighs. No interaction whatsoever necessary for that to happen, which has nothing at all to do with the quantity of matter, which is the definition of mass. So we went full circle around. We don't know if we're talking about weight or mass, whether the Higgs is a particle of weight or of mass, and we will never know because they've never defined mass or weight. They have 7 definitions for mass. I don't know how many they have for weight. So we have no idea whatsoever at all what these people are doing out there. And just in case, we throw the icing on the cake, here it is. These are Wheeler and Taylor, 2 so-called physicists, mathematical physicists, and they clarify for us everything that you ever needed to know. Okay, here it is. They say nature does not offer us any concept as the amount of matter. Mass, right? History has struck down every proposal to define such a term. Even if we could count number of atoms or by any other counting method try to evaluate amount of matter, that number would not equal mass. Okay, so after all is said and done, we have no idea what mass is, what weight is, or whether the Higgs is a particle of mass or a weight. What is the Higgs? It interacts with a field. I thought that was weight, when something interacts or pushes against something, against the scale. And they're saying mass allegedly is quantity of matter. And now they're saying no, mass is actually not quantity of matter; it's an interaction. Okay. So we're not talking about how many atoms, we're saying how much one atom interacts with a field of some kind, an ocean or whatever, some fluid, I guess. So we have a contradiction there. They have not decided what mass is or whether this Higgs is a particle of mass or of weight. And the final point here is that we look it up in the standard model of quantum mechanics, okay, and we find a Higgs. And so if you ever wanted to know what the Higgs looks like, well, it looks like, apparently, from what I can see there, it looks like a ball that's got an H on it. Like Harvard, an H. And that's the Higgs. It's got all these little numbers there we don't care about. We just want to know what it looks like. And I guess it looks like that, like a ball with an H on it. And so it's a ball that has no mass until it interacts, which means it's the particle of weight. I don't know, you tell me.